In this video, we're going to look at a Poisson distribution. So some questions or studies are based on counting a number of occurrences on a fixed time interval or in a fixed space. This fixed time interval or the fixed space is called an area of opportunity. So some examples of Poisson distributions. Some examples of variables that follow a Poisson distribution are the number of defects in a new shirt, or maybe the number of network failures in a day, or possibly the number of people arriving at a bank over a certain time period or a given time period. The example we are going to do in this video is as follows. The Department of Transportation keeps statistics for mishandled bags per 1,000 airline passengers. In September 2016, Delta mishandled 1.35 bags per 1,000 passengers. What is the probability in the next 1,000 passengers that Delta will have? And then we have three questions here. A is no mishandled bags, B is at least one mishandled bag, and C is at least two mishandled bags. These are the types of questions that we can now answer using a Poisson distribution. Before we talk more about a Poisson distribution and then try to answer this, let's first point out what is our area of opportunity here. That's our interval. And our interval in this particular example is per 1,000 airline passengers. So our area of opportunity is 1,000 airline passengers. And we know that on average, in September, Delta mishandled 1.35 bags per 1,000 passengers. But again, our area of opportunity was the 1,000 passengers. Okay, let's talk a little bit more about Poisson distributions so that we can attempt to solve this problem. Well, there are four properties that need to occur for a Poisson distribution for your instance to be a Poisson distribution, in which case then we'll have a formula on the next page that can tell us how to find probabilities related to Poisson distributions. But what are these four properties that need to hold? Well, the first thing is that you want to be interested in counting the number of times an event occurs in a given area of opportunity. We'll need that to be true. And then we'll also need it to be true that the probability that an event occurs in a given area of opportunity is the same for all areas of opportunity. And for clarification, we mean the same for all areas of opportunity of the same size. So if we look at 1,000 passengers and we see a certain probability of an event occurring in that 1,000 passengers, that's not different than if we chose a different 1,000 passengers. In this case, we are assuming that's true in this example. We're assuming that since we took the data over all of September and we got a number of mishandled bags per 1,000 passengers, this probability doesn't change if we pick a different set of 1,000 passengers. All right. So the third thing we would need is that the number of events that occur in one area of opportunity is independent of events in another area of opportunity. Again, we're kind of assuming that here, but that should make sense that those would be independent. I.e., if something happens in one set of 1,000 passengers, that doesn't really affect how the probability will change over a different 1,000 passengers. Okay, so the probability that, and the last thing is the probability that two or more events will occur in an area of opportunity approaches zero as the area of opportunity approaches zero. And what does that mean? Well, if we think about this question, what's the probability that two or more people have mishandled bags when the number of passengers that we're looking at approaches zero? Well, if we go all the way to just looking at one passenger, then clearly the probability that two or more passengers have mishandled bags out of just one passenger is 0. So this property holds in this particular example as well. Okay, so if these 4 things happen, then we have a Poisson distribution. And what does that mean? Well, our formula for a Poisson distribution is the following. This is the probability that your variable x is equal to some certain number of events, given lambda, where lambda is the expected number of events on your area of opportunity. The probability of all of that is, and here's how we calculate that. This is e raised to the negative lambda times lambda raised to the x divided by x factorial. Where again, we really just have 2 variables here because e is the constant 2.71828, and then so on. You can put in more of the decimal places there if you wish, but this is generally enough, at least for our examples in this class. And again, what is E? E is just a constant, and it is this constant right here, which is a non-repeating decimal. But our 2 variables, or 2 things that will change here, is x is the number of events of interest, and lambda is the expected number of events in the area of opportunity. Now let's go back to our example and use that information to solve this problem. So remember that again, our formula is p of x equal to x, given some lambda is equal to e raised to the negative lambda times lambda to the x all over x factorial. Well, in part A, no mishandled bags says that x is equal to 0. So the number of events of interest is 0. That we have no mishandled bags. And lambda is our expected number of mishandled bags per 1,000 passengers, and that was 1.35. So this solution is p of x equal to 0, given that lambda is 1.35, and this is e raised to the negative 1.35 times 1.35 to the 0th power, all divided by 0 factorial. Well, anything to the 0th power is 1, and 0 factorial is also 1. So this is just e raised to the negative 1.35. And that is the probability that we have exactly 0 mishandled bags in the next 1,000 passengers at Delta. What is the probability that we have at least 1 mishandled bag? Well, at least 1 mishandled bag means 1 or more. Well, the total probability of every possibility should be 1, right? That should add up to 1, right? 0 mishandled bags plus the probability of 1 mishandled bag plus the probability of 2 mishandled bags all the way up until 1,000. That whole probability should add up to be 1. So the probability that we have at least 1 mishandled bag is just 1 minus the probability of 0 mishandled bags, which is 1 minus e to the negative 1.35. All right, and what is the probability that we have at least 2 mishandled bags? Well, that would be 1 minus the probability of 0 mishandled bags plus the probability of 1 mishandled bag. So this is 1 minus the probability of 0 mishandled bags. And again, I'm not going to write lambda is equal to 1.35 here. We can We know that already, so I'm not going to rewrite that part. Plus the probability that x is equal to 1. So the number of mishandled bags is 1, given our lambda. So we find these two, add them together, and subtract those from 1. And that will give us the probability that at least 2 mishandled bags, of having at least 2 mishandled bags in the next 1,000 passengers. Well, what does that actually end up being? This is 1 minus e to the negative 1.35 minus e to the negative 1.35 times 1.35 to the first power all over 1 factorial. Where this right here is your probability of exactly 1 event occurring. All right, and this is our solution here. And of course, if you're plugging that into some assignment, then go ahead and calculate those decimals. But for here, this answer is fine. All right, and that will be the end of this video.